Welcome back, everyone. And now we move to the last session of today with engineers Hani Kamel and engineer Mohammed Rashad. Engineer Mohammed Rashad, the floor is yours.
Assalamu alaikum wa rahmatullahi wa barakatuh. Hi everyone. First of all, we would like to thank OMICRON to give us the chance to participate in such a great summit. This is Engineer Mohammed Rashad and my colleague Hani Kamel. We will discuss the Transformer Differential Protection Theory of Operation, and after that we will simulate some faults by using the MATLAB Simulink software and extract the Comtrade file from the MATLAB Simulink to use it again by the software of Test Universe 4.3 to make a re-injection on the protection relay using the OMICRON CMC356 test kit. We would start by a brief regarding the different transformer vector groups. Then we would talk about the transformer differential protection system and the stability condition for the differential protection. Then we would have an introduction regarding the transformer internal faults and the methods of protection relays testing. Then we have two case studies. The first case study regarding the transformer internal fault turn to turn, and the second case study would be turn to ground fault. And both case studies will be simulated by the MATLAB Simulink. And finally, we would see how to extract the fault Comtrade file from the MATLAB Simulink, and using this file to make a re-injection on the protection relay of cell 487E using the CMC356 test kit. Why there are different transformer vector groups? Actually, the different transformer vector groups are used in many cases and for different purposes, as removing the autoharmonics drawn by the nonlinear loads or the magnetizing currents of the transformer, providing a closed path for the third harmonics and inhibit its appearance on the primary side of the transformer, especially if the primary side was delta winding, providing a path for the ground current to indicate the ground faults, especially if the transformer side was star windings. Actually, the determination of the vector group of the transformer is very important, and that because the vector group shall be considered when calculating the transformer differential protection settings and also when connecting two or more transformers in parallel to avoid the large circulating currents. Now let's discuss the transformer differential protection system. As the differential protection is a unit protection, two current transformers must be placed before and after the protected object, which is a transformer, for example, DYN3. The two current transformers with subtractive polarity and the CT star point of each current transformer shall be towards the protected object. And this would be the final three wiring diagram where the current transformers, which are placed on the upstream and downstream sides of the transformer, are connected to our protection relay, which is the cell 487E. As we can see, the CT star points are towards the protected object, which is our transformer, while the other sides of the current transformers are connected to the dot point of the CT input of the protection relay. Let's consider the following power transformer data. Our transformer is a step-down transformer with a power of 60 megavolt ampere. The voltage of the high side would be 132 kV, while the voltage of the low side is 13.8 kV. So in this case, the current of the high voltage side would be 262.43 ampere, while the current of the low voltage side would be 2510.22 ampere. The CT of the high voltage side would be 301, while the CT ratio of the low voltage side would be 3000 to 1. During the transformer normal loading conditions, the currents would be, for the high voltage side, 262.43 ampere in all phases during the balance condition, while the angles would be 0, 240, 120. While the currents in the low voltage side of the power transformer would be 2510.22 ampere for the three phases, with angles of 90, minus 30, and minus 150. These are the values of the primary side of the current transformers, while the current in the secondary side of the current transformers, which is fed to the protection relay, would be 0.8747 for the three phases in the high voltage side with 0, 240, 120 degree, while the current in the low voltage side would be 0.8367 for the three phases with angle of 90, minus 30, and minus 150 degree. We have three important considerations that shall be taken in the transformer differential calculations, which are the different current magnitudes, the tape changer that would affect the current magnitude, the angle phase shift, and angle phase matching. Regarding the first point, which is the different current magnitudes, the protection relays can compensate for that by using the per unit values in the calculations. While regarding the second point, which is the tape changer, we can either connect the VT to the relay in order to change the base current automatically, or connecting the transformer tape changer BCD with the value of the voltage change for each tap. And regarding the angle phase shift and phase mismatching, we can use the vector group compensation matrix, which is already available in all protection relays. So in this case, the relay current which will be used in the differential protection calculations would equal to the measured current in ampere over the nominal current in ampere multiplied by the compensation matrix, where the nominal current in ampere will equal to the transformer power in kilovolt ampere over root 3 multiplied by the voltage of the side of the transformer, either the high side or low side, in kilovolt multiplied by the CT ratio of the transformer side. And regarding the compensation matrix, our transformer is DYN3, so for the delta side, we would compensate using the matrix number 0, while for the low voltage side, which is the star side, we would compensate by using the matrix number 3. Actually, we have our general compensation matrix equation, where we can get any compensation matrix from 0 to 12 by just substituting by the factor k by the number of the vector group. So in case of the 0 compensation matrix, we will put or substitute k value with 0. So we will get the matrix 0, which is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. And again, when we compensate for k by 3, we would get the compensation matrix, which is 1 over root 3 multiplied by 0 minus 1, 1, 1, 0 minus 1, minus 1, 1, 0. Now let's come back to calculate the current values that the relay will use in the differential calculations. And the current value will equal to, as we said, the measured value in the measured value of the current in ampere over the nominal current multiplied by the compensation matrix. So in the high voltage side, we have our compensation matrix, which is 0, multiplied by the three-phase current measured by the relay. And actually, as we said, that we have the full loading current is passing through the relay, so we have 0.8747 for the three phases over the nominal current, which is 0.8747 with angle 0, 240, and 120 degree. So the final values for the high voltage side as a per unit value will equal to 1 angle 0, 1 angle 240, and 1 angle 120. Regarding the low voltage side, we'll multiply the matrix 3 by the full load current also. As we said, the measured current is a full load current, which is 0.8367 over the nominal current, which is also 0.8367 with angle 90, minus 30, and minus 150 degree. So the final current or the final per unit current for the low voltage side will equal to 1 angle 180 degree, 1 angle 60, and 1 angle minus 60 degrees. These current values for the high voltage side and low voltage side will be used in the differential protection calculations. So if we would like to get the differential values, it will equal to the vectorial summation of the transformer currents of the high voltage side and low voltage side. So in this case, 1 angle 0 plus 1 angle 180 degree will equal 0. And for the next phase, 1 angle 240 plus 1 angle 60 will equal also 0. And finally, for the last phase, 1 angle 120 plus 1 angle minus 60 will equal also 0. So in this case, it is a stability condition for the transformer, and the transformer would be stable with no any tripping by mistake or mal operation of the relay. Now my colleague engineer Hani Kamel will continue regarding the transformer internal faults, and he would discuss also the case studies used by or simulated by the MATLAB Simulink.
In the name of Allah, the most gracious, the most merciful. Thank you, OMICRON. Thank you, Engineer Muhammad Rashad. I am Engineer Hani Kamel, testing and commission engineer for substation, and former transformer design engineer, and now founder also for EEEB, which interested and working on field experience sharing with electrical engineers worldwide. It's existing in social media like YouTube and Facebook and LinkedIn, and also it's available as a website EEEB-EGY.com. So back to our presentation. Transformer is very important component or part in power network, and without the right and periodic maintenance, the transformer can get failure. Transformer type changer, for example, especially the oil type, contact wears happen. So if without contact thickness check as per the type changer guide, maintenance guide, can lead to type changer failure. Pushing without periodic check, especially if there is oil leak in the bushing, can lead to bushing failure. Or if rain ingress inside the bushing, it also lead to bushing failure. Cooling, if not checked carefully, and if there is cooling failure, it can lead to overheating the transformer. And silica gel, if not checked also, and get wet, so or saturated with moisture, so moisture can go inside the oil and inside the winding, which lead to transformer failure. Failures like turn to turn inside the winding or turn to ground also can happen. So type changer also operation raise and lower, if not given right from the AVR, can lead to overfluxing and core heating inside the transformer. So we need to make sure that periodic maintenance done on the transformer to keep it right. And now for protection relays, which already protects the transformer, we need to check it's also working right. So we test protection relays. We can test it by calculated values, check the pickup values, threshold. We can use recorded fault from existing relays in the power network, or if the fault is not available, so we can simulate fault by simulation softwares like MATLAB Simulink, and then we export these files, in Comtrade files, and then we test the new relay by this fault. So our study case number 1, here we have transformer in HV winding, it's disk continuous type, and there is fault between turn to turn fault, and we can see inside the winding already got burned, and there is forces on the winding. We can see this is the fault part, fault area. Here we can see the burn due to this short circuit current. Same we can see here, and this the fault area. So our transformer here is DYN1, and this is a vector group of DYN1, and there is a fault inside 1U 1W winding. It's turn to turn fault, and here is a current flow in from 1U to winding 1U 1W and then to 1W, and this on half cycle and then reverse in the other half cycle. We simulated this fault by MATLAB Simulink, we can see our substation is 132 over 13.8 kV and 2 line feeding bus A and bus B 132 kV bus, and there is bus tie, and here we have two transformer 1 and 2, transferring volts from 132 to 13.8, and then 13.8 kV bus A and bus B, and we have some loads and auxiliary transformers. So now we can see system is running and stable, no trip, and low and loaded. Now fault happen in 1U 1W in transformer number 1 HV side. So now we can see the fault current taken from the network. Fault signal is now available, trip signal is available now in HV and LV side, and after the time delay, we can see that the breaker tripped in HV and LV and isolated the fault area from the network. We can see the other component in the network still in service and not trip, not got wrong trip or wrong operation. This case number 1, this fault already exported to Comtrade file to make it ready for relay testing, and this is the fault record of this fault. You can see the red and blue fault, red and blue current in 132 kV side, in instantaneous value and the RMS value, and same in 13.8 in instantaneous and RMS. Here we can see the differential signal, this from the MATLAB Simulink, this window, and here the reflected signal in 13.8 kV to trip the 13.8 kV circuit breaker. Second case, winding to ground fault or turn to ground fault. It's in same winding 1U 1W, and here is the current feeding from the power network to feed the fault in 1U and from 1W phase. This again back to our single line diagram. We can see system now is healthy. This is before the fault. System now is healthy and it's loaded and all breaker in service. Now we initiate the fault inside HV winding. It is as we said before, it's in 1U 1W, so the current will be in 1U and 1W phases. So we can see here 1U and 1W phase have the current, and the current also coming from line 1 and line 2 through the bus tie. It's feeding the fault, and some current going also from the other transformer because it's still in parallel operation and bus tie in service or closed. Now the breaker, it's here in this slide already trip signal in HV and LV initiated, and here we can see the breaker tripped in HV and LV side, and only transformer number 1 isolated from the network. The other component in the network still in service, both feeding lines, transformer number 2, all loads still in service, not wrong tripped, and transformer number 2 now feeding load of bus A and bus B through the bus tie. So we can see the bus tie current here. This current coming from transformer 2 to feed bus A 13.8 kV loads. Here we can see the fault current. It's red and blue, means 1U and 1W current feed it from network. It's 132 kV current, instantaneous value, and RMS. Actually, this transformer just after energize, after some time, this fault happened. So we can see this fault current, and here 13.8 kV current also. Same. We can see the differential signal in HV side. This happened here, and it come here after the fault initiated, and reflected to LV side to trip the both breakers in HV and LV side. Now we will take this simulations, we'll export it to Comtrade files. This Comtrade file we can import by Relay Tester software, which we'll use to re-inject again in protection relays to make sure that this protection relays, if this fault happen in the network in real time, it can trip and the other relays cannot will not trip. Thank you. Now we will go back again to Engineer Muhammad Rashad. He will talk about this point clearly.
Thank you, Engineer Hani. And now let's see how to replay the fault that Engineer Hani extracted from the MATLAB Simulink as a Comtrade file using the test universe 4.3 in order to make a replay for the fault using our test kit CMC356 on the SEL 487E relay. So first of all, we'll open the test modules and we'll choose the advanced transplay. Now let's open the test object and enter our data like the frequency, the nominal voltage, also the nominal current. Also, we can put the name or type the name of the relay like SEL 487E. The manufacturer is SEL. Device type is just transformer protection or transformer differential protection, whatever. And you can put the serial number, and finally you can put the name of the engineer who is going to test the relay. Then OK. Okay, so now after that we'll open the hardware configuration to check our current, the voltage terminals, any binary inputs that we are going to use or binary outputs we are going to use. Okay, or analog outputs are okay. Binary inputs, if we would like to use one binary input and voltage type or as your site condition, we can use it as a dry contact or a voltage contact. Now we will import the Comtrade file. We can start the play. Now the CMC is injecting the fault on the protection relay, and we can see the behavior of the relay. We can monitor the LED. We can check again the Comtrade file from the protection relay itself, and so on. So by this way, we can make like a simulation for the fault that we have studied through the MATLAB Simulink and simulated by real injection using the CMC356 test kit by this advanced test module offered by the Test Universe 4.3. Thank you all, and we are ready now for your questions.